Good afternoon, one and all. I welcome you to the fifth live session of the NPTEL course Oil Hydraulics and Pneumatics. The course tutor is Professor Somsekhar Siramat, and I am the teaching assistant. I hope you have gone through the lecture videos for week 1 to week 5, and based upon that, we will have a few discussion. You can also ask if you are having any doubts, and we will try to solve that. Coming to the first question. So most of these questions are taken from either the assignments of this year or previous year, or like some fundamental questions from the video lectures. Okay. Uh, so coming to pneumatics, an effective system is required in pneumatics for which of the following operations? So as we know that in pneumatics, we can't directly use the air that we are taking in from the atmosphere with the help of compressor. Like the compressed air, we can't directly use it. We need to do some sort of treatment and also put some safeguarding equipments in order to provide a robust and effective system for a pneumatic circuit. So, what are the main components or main elements that are to be included for running a pneumatic circuit? So first of all, pressure regulator. Yeah, it's very much required to regulate the pressure so that we are, storing the pressurized air at a particular pressure that is usable for that particular application. Next, increasing the air temperature. No, this is not one of the desired outcomes. Rather, it happens due to the increase in air pressure after compressing it. And actually, we need to cool it down by using an after cooler. So, this is not a correct option. Next, introducing a mist of lubricant in air. Yes, this is very much required, especially to lubricate the moving parts in the compressor or in the direction control valves. So, mm, and not compressor, sorry, the actuators and the different valves where there can be spools and other mating parts. So there you need to have some sort of lubrication which would allow smoother movements of the mating parts. Next is removing moisture from the air. Yes, this is also required so that the air that we are using is essentially dry and also clean, and that reduces the chances of you know occurrence of corrosion in the um, pneumatic parts, pneumatic components, because many of the components are made of steel. So this is like required. Removing the contaminants from air, yes, this also is required to reduce the chances of corrosion and erosion in the pneumatic system. Next, reciprocating type compressors are dominated over other types of compressors because of the following reasons. So, as you might know, that most of the compressors, air compressors that are being used are reciprocating type only. Very few are there which can be of not hydrodynamic, sorry, uh, you know, rotary type compressors. Mostly are reciprocating ones. So, why? What is the reason? So, because you get a very high efficiency of about 85 to 90% and even above. So that is one of the reason. Very high overall efficiency. Then wide range of capacity. You can handle fluids at different flow rates, ranging from like very low discharge to very high discharge by by using reciprocating type compressors. Next is wide range of pressure. Yes, the pressure range you can go from very low pressure of around 4 5 bars to up to 10 12 bars. That is also possible. In pneumatics, generally we don't deal with very high pressures, but like in hydraulics, but still we can go up to higher pressure limits using reciprocating type compressors. Only available in single stage. This is not a correct option, because we can have multi-stage compressors where suppose you need to achieve a very steep, you know, pressure differential. In that case, it's better to do it in multiple steps. So the first compressor will compress the gas and increase its pressure. Yep. And the next compressor will again compress that pressurized gas at P1 dot to a next higher level, and finally that will again pressurize to P2. So this is multi-stage compression, and that is possible by using multi-stage reciprocating type compressors, which is also available in the market. So this is not a correct option. Next, we have close familiarity by operating staff. Yes, this is also correct, because most while you are dealing with such compressors, you should be knowing what are the different moving parts, the static parts, and like disassembling, assembling. You should be thorough with it. So that's why, since the operating it is not having very much complicated uh, or integrated parts inside it, and hence is um, easy to handle by the staff. Okay. Coming to valves, so as you might have seen that valves can be broadly classified into three different categories. One is for controlling the flow, that is called flow control valve, that generally is used to determine, that generally is used to uh, supply flow at a particular um, discharge, that again decides the velocity of uh, pistons or actuators, linear actuators, or the speed of rotary actuators, that is motors. Then you have um, direction control valve, so DCVs. So this is again used to, like, this is for linear actuator, this is for motors. Okay. So in direction control valves, again, you have to like change the direction of the actuation, right, in several applications. So that can be attained by changing the direction of flow of the working fluid. So for that, direction control valves are used. It can be used to start a particular operation or stop the particular operation by modulating the flow of the liquid in the hydraulic or pneumatic circuit, and also change the direction of the flow. So that is DCV. Next, one of the most important components is pressure control valve. So as you are knowing that the fluid power, the working fluid is pressurized. It is not at atmospheric pressure. It's like much higher than atmospheric pressure, and hence there should be some components that can be used to regulate the, or regulate the pressure to keep it within the safe limits and safe and usable limits. Yeah. So PRVs are also one of the most important components. Not PRV, pressure control valve. PRV is one type of pressure control valve. So this is used to regulate the pressure, which in turn determines the actuation force or the actuation torque. Actuation force in case of linear actuators, actuation torque in case of motors. Okay. So These are the broad classification of valves. Now, this is just an overview that I gave before coming to the questions related to valves. So, yeah, what is the first question? Which of the following valves has OR logic function and AND logic function? Actually, these are two separate questions. Check valve, time delay valve, memory valve, shuttle valve, twin pressure relief valve. So anyone can you answer like which is the which can be used for realizing the OR logic? Or I guess you know that if there are two inputs X and Y, so there's a truth table for OR operation. It is basically this is the logic operation. Okay, so this is the logic operation, and you want to realize it in pneumatic circuit or hydraulic circuit. Say. Mostly, it's used in pneumatics because and these are low pressure pneumatics they use. Okay, so what does this mean basically? So if zero here means there's no flow, one means there's a flow. So suppose there's no flow from both the um, pathways or the input pathways. I would say these are basically the input pathways, and this is your output pathway. Okay. So if there is no flow from both the input pathways, then there will be no flow in the output. If there is flow from at least one of the pathways, then there will be outflow. Okay. So if you want to realize this in a hydraulic or pneumatic circuit, it generally, like if you want to draw the symbol, then it's like this. So there will be, so these are, this is a NRV, right? Non-return valve. So that allows the flow to happen only in one direction, that is in this direction. So you have two such NRVs with a common ball. Okay. So what happens when there is flow from, okay, sorry, let me name this as X and Y because I have used X and Y here. And say this is your Z, that is the output. So if flow is happening from this side, then what happens at neutral position, your ball will be sitting here. Okay. So no flow from any of the sides means the ball will be here. So no flow through Z. So when flow is happening from here, the ball gets pushed towards this side. Okay. So that allows the flow to divert from here towards Z. So this is the condition. This one. Okay. X is equal to 1, Y equal to 0. Basically, it depends on the differential pressure. But yeah, this is like if Px pressure at X is higher than pressure at Y, then the flow will be happening from X to Z. Okay. No flow will be happening from Y. Similarly, if Py is higher, then the ball will be shifting this side and the flow will be happening from here to here. So this is just the basic outlook. Now, if you want to look at the applications of this, application can be like you have two control, two control, two control systems for one particular equipment or for one particular cylinder. Suppose this is your cylinder. or actuator basically. So you want the actuator to be actuated when any of the control systems are being activated. So for that, control system means we are having two different push buttons at two different locations. So either if you also push it, then also the flow will take place. If any other person from the other end also push it, that flow will take place. So to realize that, we will be putting one shuttle valve here. So okay, we didn't come to the question. The question asks which of the following valves can be used to realize this OR logic function. It's a shuttle valve, also known as double check valve. Double check valve because it contains two check valves as I had shown. So if you look at the circuit, it looks like this. Okay. Now will be connected to one push button. This is a spring loaded manually controlled push button switch. Say S1, and again like you have, this is normally closed, no? So I should be denoting from here rather. So you have another push button on this side. Okay. So now these are also connected to your power pack, and the other one to the tank. Like this is T port, this is P port. Now, if you look at this carefully, if you are activating any one of the switches, that is S1 or S2, suppose you activate S1, you push this switch, what happens? This configuration comes into play, and the flow will take place like this, from here to here to here. Sorry, I'm just unable to delete this small red line. Anyway, I hope you understand. This won't be. So what happens? This ball was initially say in the near the middle. It gets shifted this side, and the flow will happen from here. And what happens? This cylinder will extend. Okay. Now that is one of the cases. Now suppose like once you release this switch, since this is spring loaded and this actuator is also spring loaded, it will retract back, and this is already like S2 is off. So what happens now? The flow will be directed through this port to the tank, right? Now suppose both S1 and S2 is open. In that case also flow will take place, but there can be some conflicts. Like in this case, although the flow is taking place, not through any uh, pilot, it is not a pilot control valve. Still, there um, there can be some conflicts. Okay, so this is the OR function. Now, if you want to realize the AND function, so I hope you understood. Any one of the two S1 and S2, any one of the two valves can be actuated to actuate this, but to move this linear actuator. I think someone just raised his hand. You can unmute and ask if you are having any doubt.
Yeah, hi.
Yeah, hello.
Well, I have no doubt. I just wanted to add that this system is called pneumatic, and it's commonly used in industrial uses. So I had to mention that it's an important system.
Okay, okay. So, do you have anything else to add to this? Like, if I have missed something.
And no, thank you. You're doing great.
Okay. Oh, okay. So, coming to the AND logic function. So, this is the OR one. So, this was the truth table for OR. Now, if we look at the AND function, then these values will change. Right? X dot Y. So, again, zero means no flow, one means flow. Okay. In AND function, if any one of the input value is zero, then what will be the output? It will be zero, right? So in the first three cases, you will get zero, and the last one you will get one. So if you want to realize this in any pneumatic or hydraulic circuit, how will it look like? Or first of all, the first question is like which of the following valves are manifests this particular thing? Anyone? Check valve, time delay valve, memory valve, shuttle valve. We already discussed it. Used to realize the OR function. So the answer is twin pressure relief valve. So it basically looks like there is a symbol. I hope you know what is pressure relief valve. Okay, so this is the input, say X. This is another input, say Y, and this is your output Z. So in this is designed in such a way that both X and Y should be having inflow so that you get an outflow from Z. Okay. Otherwise, if any one of X or Y is not having a flow, then there will be no flow through Z. This is again necessary. Like you want to put an additional, security to your hydraulic system. Security means suppose there should be some switch that needs to be turned on simultaneously. There needs to be two switches. Suppose one safety switch is there and another on switch is there. Say so, you need to press both the buttons to actuate the particular system. So, in such cases, you can use this twin pressure relief valve that allows you to realize the AND logic function. When there is no flow from any one of the sides, then there will be no flow to the actuator. Poppet valves are responsible for which of the following? Okay, so I just discussed in the previous slide that valves can be broadly classified into pressure relief valve or pressure control valve, flow control valve, or direction control valve. That is based on the functionality, the function of the valve, what function it does. If we look into the design perspective, like what goes inside the valve, what is the construction, then it can be divided. It can be classified into broadly classified into poppet valves, spool valve. Can you name a few? Did I miss out one? Yeah, I'm just asking something like, did I miss out anyone? So there is another type of valve, that another classification. It's rotary sliding valve. So in poppet valve, you basically have a poppet. It can be like, generally it's conical in shape and it sits on a rest. This is a simplified design that I am showing. So from this direction, the flow is coming. If the pressure of the fluid that is flowing from this direction exceeds the fresh pressure of the spring, then this poppet will lift up and the flow will be happening from the sides. So this can be replaced by a ball type. It depends on what applications. Okay. So again, same principle. If we look at spool type, then what's the major difference? You have a cylindrical spool, which is having these areas which are cut down, that is called groove, and these areas are called lands. So this particular distances, relative distances, I would say this I would rather not write x and y, or else you might get confused. Let's say it's L, L1, L2, L3. There's L1, this is L2, this is L3, and you have say B1, B2, B3, or B2. Okay. So what happens? This cylindrical body, it's installed within a hollow cylindrical housing. And what happens? And there will be ports inside the housing at and different spacing, relative spacing. So as this spool, this is called spool, and this is the casing on the outer side, and these are the ports. So the spool is translatory. It can translate within this particular casing, and from the relative position of this particular landing and the groove, you can understand that suppose this is my pressure port, that is the pressurized fluid is coming from here. It can be directed either to port A or to port B. If this particular land is here, say, then the fluid flow won't be happening to port A, rather it may happen to port B, and there is some tank port T. So likewise, you generally design this spool type valve. I just gave a very simple example. Next, you have rotary slide valve. There also you have ports that are cut out on circular bar. So there will be uh, one rotating body and an outer casing. On the outer casing, you will be having the ports, pressure port A and B ports, and on the inner side, you will be having like this. So these are all like this is rotating body, and these are connected through these channels. So again, depending on the relative position of this particular outer casing, which is having the ports and the inner rotating body, you can achieve different uh, flow directions, pathways. So that is rotary slide one. Depending on the applications, you can choose which is more suitable. So in this particular question, it asks about the properties of poppet valves. So each valve, each of these three configurations have their own, come with their own advantages and disadvantages, which includes the ease of manufacturing, that is called manufacturability of the valve, then maintenance, then longevity, and what pressure it can sustain. So and again, like compactness. So many such properties come into picture. You have to choose accordingly. So in case of poppet valves, what are the options that are given? Zero leakage in closed position. This is true because the poppet it snugly fits over this fitting, and if this particular spring it is having high stiffness, so if this sits over like there is a positive contact between this portion and the poppet, then this landing, this is called the landing, and there is a positive contact between these two, then you can ensure that there is zero leakage. So in closed position, this is positive contact is there, and hence you can ensure minimal or zero leakage, almost negligible. And then poppet elements stick when left under pressure for long periods. This is wrong because this contact area is not high enough for this thing to happen, or the sticking to happen. Axial pressure balance is possible. So, what is your opinion on this? Whether in poppet valves we can balance the axial pressure? What is your opinion? I am asking you. Can we balance the axial pressure? There will be some pressure imbalance that can't be avoided. So pressure imbalance in the axial direction. So axial pressure imbalance will be there. You can get rid of that by uh, you know some means, but generally it can't be avoided. Like, so there will be imbalance. So I will rather not take this point because there will be axial pressure imbalance in poppet type valves. Next, fast and consistent response time. Yes, this is also true. Approximately 10 to 15 millisecond is the response time. Response time is basically the time gap between between the operator pressing the switch or actuating it and the response, that is the flow. So that gap is basically called the response time. Suppose I'm just showing here. This is the input, okay, 0 and 1. So this is switch off, and you switch on at this particular instant of time. And if you look at the response here, like this is your input signal and this is the flow. So there will be a small delay between the input and the response. Okay. So this was your input, this is your response. So this particular gap between the input and the output is called your response time. So this is very less and it is consistent. Like after every cycle, it won't be changing. Okay. So that is why it is more reliable, this type of valves. Uh, and as I said, it will be in the range of a few tens of microseconds. One poppet valve is sufficient for many flow paths in the circuit. This is not correct because in one using one poppet valve, you can't control multiple flow paths. You can control flow path only in one direction. We can't control multiple flow directions using one poppet valve. So this is again not correct. So axial pressure imbalance is there, but there are some remedies to overcome that. I would encourage you to identify a few of them so that we can take it up in the next class. like how to go about this axial pressure imbalance, how to achieve this balance. Next, this is a small, numerical. I won't say numerical, rather uh, numeric. I mean, you need to derive something. So that makes it little bit more interesting in the theoretical parts. Which of the following equations hold good for regenerative neutral, where QP is the pump flow, AP is the piston head side effective area, AR is the rod side effective area, and P is the pressure. What is this regenerative neutral that we are talking about here? First, you have to identify that. What is it? What is the regenerative neutral? Anyone? Hey, am I audible? Once I'm presenting, I'm not able to know whether thing is there or not. Can anyone please confirm if I'm audible or not? Okay, thank you, Lokesh. So, yeah, what is regenerative neutral? So, when we talk about 4 by 2 direction control valves, what is 4? 4 is the number of ports or the number of flow pathways, and 2 is the number of position. So, when we talk about 4 by 2 DCVs, a simple valve. So, here you have the pressure port and the tank port, and the A and B ports that goes to the actuator. In this case, this is connected to the pump, say, the power pack. This will go to the tank. Sorry, this is for exhaust, what I had drawn just now. And this will go to double acting cylinders, say, A and B. Now, see, suppose till the pump is on, as we push the switch, it will extend. If we release the switch, it will retract. Right. So if I keep the pump on, it will continuously extend. In either configurations, whether in this particular configuration of the ports or in this particular configuration of ports. By configuration, I mean the positions. There is no such position that will hold your extending or retracting, function of the double acting cylinder. So for that reason, we introduce another position in between, that is called the neutral position. And there are different, neutral configurations like closed center, open center, tandem center, float center, regenerative center. So regenerative center, one second. Regenerative center means your pressure port will be connected to both A and B, whereas the tank will be isolated. So let's talk about the neutral position now. So for that reason, I have to erase this activation position. This is now connected to pump, and these two are connected to either sides of the double acting cylinder. Now you haven't switched on anything, and so in this case, for achieving the neutral position, you need to have like the other extreme position, you need to have another switch for this particular configuration. Anyway, so talking about the neutral position, this is your basically regenerative neutral. Why we need the neutral position um, to stop the continuous extension and retraction position. You need some interference, and for that you put this neutral position. Okay, so as you can see that in this condition, I am just going into a little bit theory before I derive this. So what happens, as you can see, suppose your cylinder was attached to some load. Okay, so load means there will be some pressure on both sides of the cylinder while you are extending it or retracting. So suppose during your extension operation, you like for extension you have to push this. Now your cylinder, sorry, the pump will be connected to here, and this the configuration will be like this. So in that case, and the cylinder would be extending. Now, if you want to stop it at a particular intermediate position, then what you do, you release this, and it will come back to this neutral position. So under this condition, what happens? Your pump will be pushing the liquid to A and B ports. But what happens now that there will be, um, you know, like this regeneration phenomena happening. So what is that? So this this actuator was extending. So suppose the velocity of this particular piston, I'm saying it's VE, or the extension velocity. So there will be some discharge from this particular port that will merge with the discharge from the pump. Suppose this is your QP and this is your QR, and that goes into this portion. Okay, so sorry, P is your piston side. I mean this side, and R is your rod side. So let's stick to that nomenclature. Okay, QP is the pump flow. Then I would so rod side area. AR is the rod side area. AP is the piston side area. Okay, so this is a QE. So basically, I can write QE is equal to QP plus QR. So this is the regeneration. Why? Because this is the extra flow that is getting added to the pump flow, and during the extension, you are getting an additional boost. That is this one. So if you look at the extension velocity, it is nothing but QE by AE, right? AE means this side of the piston. I would that is denoted here as AP. So it's basically QP plus QR divided by AP. Any doubt till here? This is the extension velocity. Okay. Now, if you look at the value of QR, QR is the amount of liquid that is coming out through here. So Q is again area multiplied by velocity. So area on this side is nothing but area of piston minus area of rod multiplied by VE multiplied by VE. Okay. So if you substitute this particular QR over here, I will arrive at AP into VE is equal to QP plus AP minus AR into VE. This and this will cancel, and what you will get is V is equal to QP by AR. Okay. Okay. So this is the extension velocity. As you can understand, that is AR, that is the rod area, that is much less. So your extension velocity will be much higher. This is much less. Okay. So in this question, VP has been denoted by velocity, this VE. Okay. VP is QP by AR. So this is the correct option. Any other options are correct or not, we have to see. So what is the regeneration force? Regeneration force is your, so suppose this is your cylinder. So you have pressure on both the sides that will be acting. So this side it will be like the force that is acting on this face, that will be basically P into AP. And the pressure here, under this condition, it will be at the neutral condition, pressure on both the side will be same, minus P into AP minus AR. Pressure multiplied by area is force. So what did you get? We'll get P into AR. This is your correct option. Okay. So this is the regenerative force that you're getting additionally. So what happens when, as soon as you're bringing into the neutral position, this will extend very fast and it will hang on there. Then suppose you push this button, it will retract. Okay, coming to the next question, differentiate between pilot to open and pilot to close non-return valve. So we have already discussed what is NRV. It is basically a flow control. Yeah, so it is basically a direction control valve. So what is the difference between your pilot to open and pilot to close? If you are taking the feed, like the pilot signal from the downstream, and based on that you are allowing, so at that time this will be adjustable, so there will be some spring mechanism here. So if you are taking your pilot or the pilot signal from the downstream, then it will look like this. If you are taking your pilot from the upstream, it will look like this. Okay, so one is pilot to open. Pilot to open means based on the pilot signal, their valve will open and it will allow the flow to happen from say A to B. And you have a pilot to close valve, so that will like that will close the valve and that will like restrict the flow based on the pilot signal. So that is the main difference. Now if we talk about the application part, then give me 1 second. Okay, so Yeah. So let me just draw it here once again. If you're taking it from the upstream, in that case, you're taking it from the. So this is the downstream, this is the upstream, and this is your A and B ports. Okay. So in this case, it's pretty simple. Suppose if there is no pilot signal, so I'm denoting it by Z. If there is no signal at Z, then signal means I would say that the pressure at Z. If you don't have sufficient pressure at Z, then this will act as a normal check valve. It will it will restrict the flow in the backward direction, and in the forward direction it won't restrict the flow. So if there is no signal at Z, then normal NRV, that is A to B is possible, B to A is not possible. But if you have sufficient pressure at Z, so I am denoting it as Z tick. So there is a signal at this pilot line. If the value of PZ is sufficiently high, then due to that spring mechanism that I showed, generally it's not shown here, but yeah, due to that mechanism, what happens is it allows the flow to happen from B to A, and A to B is anyway it is always possible because it will pop up. This ball will pop up on this side, and this will anyhow take place. But B to A will also take place if there is a sufficient pressure at Z, that is the pilot line. So that's why it is called pilot to open. That is, it opens up the flow from B to A. Next is pilot to close. So here, if again there is no signal at Z, so this is my Z line, then it will act as a normal NRV, that is A to B is possible, B to A is not possible. But if there is a signal at Z, that is the value of PZ is sufficient, then A to B flow is restricted. B to A is anyhow restricted. That is always true. So this is the new thing that is happening. Like on contrary to the normal operation. So this shows that the valve is closing. So that's why we call it a pilot to close valve. This is pilot to close NRV, and this one is pilot to open NRV. Okay, this is the difference, functional difference, I would say. Okay, a few more theoretical questions. What is a hydraulic lock? What is hydraulic lock? It happens in spool valves, right? Spool type valve. This particular phenomenon is dominant in such valves. What is it? So in spool type valves, you have a spool. It can be rotating, translating, or both. And generally, there is a clearance. Otherwise, how will it translate it? But using this particular valve over longer periods of time may lead to thermal expansion or distortion of this particular spool, which is sliding on this casing or the housing, let's say. So what happens is, since the hydraulic fluid that we are using, if it's oil, it is getting heated up over the operational time, and hence that leads to some sort of thermal distortion of this particular spool. Okay, so there may be some region where there is some sort of sticking happening between the outer casing and the spool while it is sliding. So during the sliding condition, it is trying to stick to it. So that is basically called stick slip phenomena. It is sticking again. It is that contact. Suppose you look at the micro level. So these are the two surfaces, the two mating surfaces. So as it is translating over this surface, so there at this pointed tips, the pressure is the contact Hudson contact pressure is very high. So they tend to get welded at this particular points due to the Hudson pressure, and as a result, they stick with each other. Now, as it is sliding due to inertial motion, this particular contacts again break. So it slips at that point of time. So that type of contact is called stick slip type of contact. It happens between the spool and the valve body or the casing that I was saying. So as a result of this, what happens? Like this type of the profile generally it may get changed. So if you, I'm just exaggerating the thing here. It is not the tapering may happen in the spool. So it is not this much, but yeah, this is the exaggerated view. So if say this is the direction, flow direction, or I would rather say that this is the pressure side. Suppose P1, higher pressure side, and this is the lower pressure side P2. So if you look at this particular section from here to here, this is a diverging section, right? Where the fluid is flowing. So in this diverging section, what happens? The dynamic head reduces and the pressure head it increases. Due to the increasing cross sectional area, velocity decreases and the pressure increases. Due to this increasing pressure, it pushes this particular spool further onto the valve body. So it is subjected to very high transverse forces. If you look at the front view, so the transverse forces are significantly high, and as a result of that, this particular phenomenon becomes more pronounced, and as a result, this tends to lock on the surface. Like this sliding motion is getting hindered due to this locking, and the frictional forces obviously the frictional forces also become significantly higher, and hence we call it hydraulic lock. Okay, so I hope I was able to explain that. You can expect such small questions in the theoretical portion, and this particular force, this Ft, it is directly proportional to the differential pressure, that is the difference in pressure on either sides, P1 and P2. It is also directly proportional to the this particular diameter of the spool and this particular length, that is L. and it's also proportional to another factor, that that is the ratio of P upon E. So what is this P? P is basically this taper, like how much taper has happened. Suppose the spool should be ideally this one, but due to some, manufacturing error, or due to prolonged usage, this thermal distortion may occur, and it has got tapered like this. Okay, so this particular value is what I am noting as T, and E is basically the eccentricity. So it is the distance between the center line or the axis of the spool and the axis of the valve body. So if this was your valve body, so this would be the axis of the valve body, and this is the spool, and this distance is called E, that is eccentricity. So higher the value of this P, higher will be the transverse force, and more intense will be the hydraulic lock phenomenon. Okay, coming to the next question. How is the rate of leakage related with the clearance and overlap in spool valves? So, as we know that spool valves are continuously subjected to leakage because you have sliding parts. That is, the spool itself is sliding, and for sliding, you need to put some clearance between the valve body and the spool, and through here, the leakage is happening. I am denoting it as QL. Okay. So, generally, so what is this? So this is the clearance that I am talking about. C, and what is overlap? So in spool valves, you these are the this is the spool landing, and you also have the ports through which the pressurized liquid will either flow in or it will move out of the valve. Right. So suppose this is the port. The width of the port, or the diameter of the port, is say 5p. I would say width rather than diameter, because it depends on the shape. So this particular width is WP, and the spool width is WS. Okay. So in this case, you can see that WS is greater than WP. So there is some overlapping, right? So like if the spool moves by a distance WS, then only the fluid flow will take place, either from this side towards and inside the valve or out of the valve. So there can be other conditions also, like WS equal to W, how you are designing the spool and the ports. And again, depending on this, your flow characteristics will change. So in this case, you will be having null cut valve, null cut condition. In this case, you will be having overlapping condition. And in this case, you will be having underlapping condition. And accordingly, as you can understand that the flow through this particular port inside the valve, it will also get affected by the three conditions. So if we look at the overlapping condition only and try to see how the rate of leakage is dependent on this overlap, intuitively you can understand that higher the overlap, lesser are the chances for leakage. Lower the, like higher the underlap, more are the chances of leakage. I am repeating it once again. Higher the overlap, that is, if WS is more than WP, lower will be the chances of leakage. So this is what I am trying to say. And secondly, so this is if I try to plot it, there were some experimental plots. So from the experiments, it was found that as we are increasing the overlap, the QL is reducing. This is how QL depends on the overlap percentage or the overlap metric. Now, if we look at the clearance, so that also plays a major role. Clearance is this. This is the clearance. That is the radial distance between the spool surface and the uh, outer casing surface. So if we increase the clearance, again QL will increase. So that is also intuitive. I'm denoting it as C. As C increases, higher will be the QL. If you look at it graphically, so if you increase, so this is for clearance 1, this is for clearance 2, this is for clearance 3. As you increase the value of clearance, your QL value will increase at any overlap. Now let's solve one circuit problem. Okay. So till now we were just discussing the theoretical portions mostly. Now we will take up a hydraulic circuit, hydraulic or pneumatic circuit. You can expect this type of questions in your exam also, NPTEL exam. So the question says a pneumatic cylinder in a transport system has to push a trolley to its desired rail with a precondition that the cylinder will start advancing after a time delay of 10 seconds. You have to note this. After a time delay of 10 seconds, and then it will retract to its original position after 5 seconds. So as soon as you are seeing this this word time delay or this term, what should come to your mind? That you should be using some sort of delay valve, time delay valve. Okay, so we'll see how it can be done. So draw the schematic pneumatic circuit and explain briefly. So you have a cylinder, pneumatic cylinder. It will start and advancing after a time delay of 10 seconds. Okay, so let's start from the power. So after this, you are having a funnel. So this is one of the important components. Next, be going to one valve. Since you're working with pneumatics here, you will be using this symbol to denote exhaust port. So there is no tank port here. And this P is the pressure port. So you can, one more thing that needs to be addressed here. The cylinder will start advancing after a time delay of 10 seconds and retract to its original position after 5 seconds. So the retraction is sequenced after the advancing or the extension of the cylinder. So there should be some switching, like there should be like once this particular cylinder is extended to its extreme position, then the retracting sequence should also be activated. So there should be some switching. So I am denoting it as S1 and S2, and in this particular I don't have enough space here. We'll first complete this circuit. Okay, so now if you directly connect this to this cylinder, then it would be like um, normal normal extension. But the question asks that once you activate this particular valve or switch, it will start advancing after a time delay of 10 seconds. You should put one time delay valve. So how does a time delay valve look like? It will be one flow control valve followed by what is this? This is an accumulator. So what is the work of this accumulator? It fills up with the liquid and sorry fills up with the gas, and after it has filled up, only then will it allow the gas to move forward. So using this particular thing, we are activating another valve. Okay, so now let's just analyze the first part of the problem. So whether it is starting after 10 seconds and how. So this entire is your time delay valve. So as we switch on the so this is switched on, you are getting compressed air at this port. Now suppose this S1 is switched on, this particular S1. Initially it should be switched on. So what happens? This particular thing will be activated. This configuration will be activated rather than this one. One second. So yeah, now the pressurized gas will be flowing from here through here. So here it can't flow because this will be checked by this NRV, on return valve, and it will flow through this metering circuit, or you know the stroke valve. Next, it will go and fill up this accumulator. So this accumulator is designed in such a way that it provides a delay of 10 seconds. After 10 seconds, after this has filled, flow further, and it will provide a pneumatic signal to this particular valve. So till now, what this valve was connected like this. Hmm. Now what will happen, as this is getting activated, this configuration will come into picture. And now this oh shit. Now this particular configuration is also on, so this is also getting shifted here. So that I just forgot to mention. So what happens now? Now flow will be happening from here to here. Okay. Hmm. Or we can do one more thing, like if this is getting a little bit confusing. I think this is also correct. Yeah, this is also correct. So yeah, once this has filled up, Then this signal will go, and this configuration will be taken up, and the gas will be flowing like this into the cylinder and allow the cylinder to extend. So our first part of the problem is solved. Now it says that after it has reached its advanced position, that is the extended position, then what will happen? It will wait for 5 seconds and then retract to its original position. So we have to use another time delay valve that will delay the retraction process. So okay, so that can't be realized using this. So you have to use another valve. Okay, so I made a mistake initially because I saw the two problems separately. You should be seeing the entire one. What happens? This signal will be used to, you know, activate or another valve. Okay, so I'm getting some constraint here. Wait. Hmm, I have to draw very small. So starting from the FRL unit and the power source, next it will come here. Your the center is your time delay valve for 10 seconds. So after 10 seconds, like this particular configuration. So yeah, now I could directly connect this to my cylinder. But what problem it was creating? I was not able to control the retraction process. That 5 seconds of delay. So for that I need another valve. So let us put one more DCV here. So that will allow me to control that retraction process also. So this signal will be for the extension. This signal will be for the retraction. So generally this is made as a dotted line rather than firm line. You should see that this particular lines are like center line. Okay. However, these ones are dotted lines. So these are all standard. Like I am not doing it randomly. It's a standard. Okay, and here you have a Okay. So from here you will go directly to the cylinder. You have S1 and S2 as the two extreme positions. Now, now you can understand that during the extension process, let me just recap once again. From here, if this is getting activated at S1, this is a trip switch. Once this is activated, this configuration will be withheld and the flow will be happening from here to here. Again, from here, there will be no flow due to this NRV. So it will slowly flow from, like it will be metered out through this particular orifice and it will fill up this accumulator. So that thing takes around 10 seconds. This accumulator is designed in such a way. Then it will give a pneumatic signal to this particular valve. What will happen now? This particular configuration will get activated. So this will be now here. This won't be here. So now at this point of time, previously it was here because that is the neutral position. Now what happens? From here, the signal will come. Like pressurized air will also come from here along with this side, and it will go here. This is also connected to this line. It is already pressurized here. So once the signal is coming here, this particular configuration will be assumed, and the pressurized flow, like air will flow from hydraulic cylinder, and it will extend. And as soon as it extends and reaches its extreme position, it will trip upon S2. Now what happens? You should have another such switch like this one for the retraction to take to start. So I'm drawing it here. This is your S2. Okay. You'll also have same type of config. I'm taking pressurized air from here. Next, what it will do, same like this, you will have another time delay valve. Okay. So I'm just drawing it once more. This is your NRV and the orifice. This is your accumulator, which will activate one more valve. This is connected here. And this entire is your time delay valve for this accumulator is designed such that it provides a delay of how much? 5 seconds. After 5 seconds, what happens? Okay, I just drew it in the wrong place. Yeah, 5 seconds. So after 5 seconds, what happens? The air will flow and uh, it will provide the pilot signal to this valve. And this particular port configuration will get activated. This will be now here. And from here, it will flow to here. Now, previously it was this configuration. Now, as this clips upon this S2, this particular piston clips upon the switch S2, this gets activated. From here, the flow will take place. Then it takes some time to fill up the accumulator, which is designed in such a way that it provides a delay of 5 seconds. Next, it will activate this particular configuration of the valve. This is also a direction control valve, 3 by 2. So now the air will flow from here to here, from here to this side. And this particular port configuration will be realized now. And as a result of that, what will happen? I'm just rubbing this out. This will be my new port configuration. So flow will be taking place from here to here. This is for the retraction cycle I'm doing from here to here to here, and it will push it this way. As it pushes this way, it will retract back, and the air will be exhausted out through here. So this is your circuit. So generally, you have to draw only the either the retraction or the extension. Generally, we draw the retraction position only, and you have to show like any one of the cycles, either during the extension cycle or during the retraction cycle. So here, previously I drew the extension one. Now I had drawn the retraction one. I hope you understood. Now coming to the next question. Mhm. Coming to the next question, draw the pneumatic circuit for the following task. Draw the pneumatic circuit for the following task. The in and out stroking speed of a double acting cylinder should be adjustable by choking the air supply. Start by plunger T1 and in stroke by plunger T2. Pressure monitoring of both chambers by pressure gauges should be there. That provision should be there. Develop a pneumatic control circuit for input choking and exhaust choking. First, let's do for the input choking. So we have a double acting cylinder, and the extension or the retraction should be controlled by this choking operation. So choking operation basically means you have a flow control valve or choke valve. So the configuration or the placement of the valve should be in such a way that it produces either input choking or it produces exhaust choking. So first input choking I'm doing. So you have a double acting cylinder. This is your input. So as you can understand that if you are doing input choking, which means that the suppose the when the cylinder is extending outside, that is coming through here for the cylinder to extend, that should come through a metering circuit, right? Whereas if the flow comes in the opposite direction, it shouldn't be restricted. So your NRV should be placed like this. So you can understand that when the flow is for the extension, and the flow is coming here, if it goes through this, it will get restricted. It has to flow through the metering circuit or the choke valve, and then it will flow into this thing. And yeah, so I will just remove this arrows. Generally, you don't require arrows in hydraulic in this pneumatic circuits. And I'm putting one boundary box here. This is a flow control box. Now, what about I'm just increasing the size of this cylinder. This is for the out stroking. What about the in stroking? That is the retraction stroking. That should also be adjustable, but through input choking, not exhaust choking. Like when the retraction will take place, the air will go in this direction. It will flow in this direction. It will flow out here. So that time there will be no exhaust choking. So it will directly flow through this particular valve outside into the exhaust port. But as the air is flowing in, it should be choked. So for that, we have one flow control valve and one NRV that restricts the flow inside the cylinder but doesn't restrict the flow out of the cylinder. So this is your input choking all done for this particular cylinder. Now it is basic, like you have to just connect this to uh, 5 by 2 DCV, that is like standard. Suppose I'm not drawing this as of now. Let's draw the this is the pressure port. Okay, mistakenly. This is your P, this is your E, this is your A and B ports, and this should be connected to the power supply. Now we are told about like this plunges T1 and T2. So based on T1 and T2, uh, like you should start by plunger T1 and the next plunger T2. Okay. So for extension, you should be using plunger T1. So plunger is basically this mechanically actuated, 2 by 2 DCV. So under neutral condition, it will be like this. This is a pilot signal for this particular valve, this DCV. So there should be another pilot signal for the T2 plunger. Here also I am showing the neutral position. Now all the pressure lines, this P lines or all the valves should be connected. This is one pressure line, this is one pressure line, this is one more pressure line. So all these three will be connected to your power supply. So before the power supply, so after the power supply line, you have this FRL unit that filters the air. Okay, so this is your T1 and T2. And you can understand that while we are pressing T1 first, the flow will come and to this side. Next, this particular configuration will get activated and the flow will flow through this metering circuit. So through this valve and slowly it will extend. Okay. Next, after it has extended, when you put this T2 plunger, then this particular configuration will be active and from here it will flow to here, and this particular configuration of ports will be there and it will flow through this particular metering circuit, which is again in input choking, and it will flow here. So that is the retraction. This is how it is going to work. Uh, Again, when you are drawing the diagram, you should draw it either for retraction or for extension. You shouldn't confuse between the two. Okay. Now, about the exhaust stroking, I will draw it on this particular diagram only. So I'm just erasing. It's already too much clumsy. Let me draw another diagram. It will take less time. Okay. Now I'm starting from bottom. You have the power source, then your FRL unit. Now you should keep in mind that your outward flow is to be choked. Here the inward flow to the cylinder was choked. Now your outward, that the flow out of the cylinder, out either through the extension or the retraction side, that is through port to port A or B, that will be choked, not into the like inward, not inward flow. So this is your FRL. Now you will have one plunger here, P and this T1. Having another plunger here. Okay. Next, next what? Next from here you have to give two pilot signals into a 5 by 2 DCV. So why 5? Because there are 5 ports. One port is for this particular pilot signal, and 4 ports. One for pressure, one pressure port. 2 exhaust port will be counted as single exhaust port, and A and B. So total 5 ports. Sorry, I'm sorry. This is also pressure port, exhaust, exhaust. This is your A and B. Now you have to do the metering, but you have to keep in mind that your outflow is metered rather than the inflow. So you should be placing your NRV like this, so that the inflow is not metered, but the outflow is metered. Because outflow won't be happening in this direction and inflow won't be happening in this direction, and hence directions are different. This is the only thing that will be different from the first one. This side also same. And these two will be connected again to the two sides of your cylinder, double acting cylinder. Okay, so these are your flow control valves. FCV1, you can like, generally while you're drawing the circuit, you should be um, numbering them. Okay. Did I miss out something in this question? Okay, this one I didn't do. So you have to do pressure monitoring of both the chambers. So both the chambers means for this chamber also, for this chamber also. So for that, what you need to do, you have to put two pressure gauges. That's it. So I'm denoting it with a different color. So here you put, okay, let it be. I'm just showing here. So one pressure gauge here, P1, one pressure gauge here, P2. Similarly, here P2 and P1. Okay, so this was the circuit. I hope that you had understood this. If there is any doubt, you can ask me now, or you can also ask in the NPTEL portal. Yeah. So, do you have any doubts? Anyone? The class got extended a little bit today because I started late, and yeah, these circuits are a little bit. You need to be careful while drawing them. So, I would encourage you to practice more such pneumatic circuits for different applications. Like each of the valves have different application. If you go with different pressure control valves, there are pressure regulating valves and unloading valve. Each are having different applications. You should go through each of the circuits because you can expect such questions to come in the exam. And this question, as you saw, it is not a directly framed question. You have to think where to place the accumulator, where to place this particular time delay valve. So these things will come with practice only. Okay. So let's conclude today's session. Are you comfortable with the sessions? Just a feedback from your end. So yeah, nobody is interested in unmuting and answering. Anyway, let's conclude today's session. Thank you for attending. We will again meet next Saturday